Yes, we do. Where's I gotta shut off?
Yeah, I made it so
Okay.
it doesn't cut off.
You're amazing, Allison.
No.
Raise.
Thanks a lot.
Is it the Google slides?
Oh. Oh, yeah, we have to activate it,
sweet.
okay.
When you guys after my. Oh, yeah.
It's okay. Okay, so welcome everybody to the senior design final presentations for 2023-2024 academic year. In the audience is Professor Schickel, who taught the class part of the course, and Professor Reich and Professor Algebra, who are also discipline-specific advisors. Professor Grossman's joined us online. Thank you for coming for all our guests online. So we have 3 different groups that are going. Each group has 5 minutes per person, plus 5 more minutes per group. So that means 2 groups will have 20 minutes and 2 groups have 25 minutes and 1 has 30 minutes. So after each group goes, feel free to ask questions. And that goes for people online also. You can either type your question in the chat, so be sure to look for questions in the chat, or I think if you speak up, we can hear you as long as you're not muted. So feel free to do it that way also. So without any further introduction, we have our first group. So please go ahead and take it away.
Ready? Hello, we're Across the Street Engineering, and we're here to talk to you today about the Eastgate Development Project. We are led by the following disciplines: Transportation, Jolie Overstreet; Structural Steel, Isabella Palomero; and Structural Concrete, Chance Troxa; and myself. Sorry, the lights threw me off for a second. Yeah, that's fine. And myself, Water Resources, Allison Johann, and I'm also the project manager. As a bit of a reminder, this is our project responsibilities. We've been tasked with, in orange, transportation facilities connecting Silhavy and Sturdy Road, as well as pedestrian facilities and a parking lot to accommodate the new academic building seen in gray. And then in blue, we see the water resources portion, which is managing stormwater runoff. To start us off technically, I'll pass it to Jolie Overstreet.
Thank you. So Allison kind of just briefly went over my scope for the transportation side of the Eastgate development. So just to remind you guys, I was in charge of designing the new roadway between Sturdy and Silhavy Road, and this will be referred to as the Chapel Drive extension. And along this extension will be pedestrian facilities. And after that roadway was designed, I also analyzed and designed new intersections at Chapel Drive and Sturdy Road, as well as at Chapel Drive and Silhavy Road. And finally, I was tasked with designing a new parking lot for the university building that will be developed on the Eastgate site. So the first thing that I kind of looked at was the design criteria. So all of this design criteria meets the standards of the Valparaiso city standards that are posted online, with the exception of the lane width. The city of Valparaiso outlines that they would like a 20-foot lane width. However, we spoke with the city engineer and they approved a 12-foot lane width for this project because we won't need any on-street parking here. And so with that, we can start to take a look at the typical sections. So you can see that there's 1 travel lane in each direction, both of which is 12 feet and has a 2% cross slope. And then over on the right side of this image, which would be the south side of the road, is an 8-foot multi-use path. And both of these use an HMA typical cross section per the Valparaiso city standards. And you can also note that on these typical sections, all of the water would drain to the ditches that take place off the roadway, but in between the roadway and the multi-use path. Looking at the Sturdy Road intersection, so we opted for a signalized intersection here, then that provides a level of service B for the vehicles using this intersection. And on each corner is a 35-foot turning radii, and the deceleration lengths, taper lengths, and storage lengths for each of the legs of the intersection were designed via the Indiana Design Manual. Hopping over to the other side of the project. That's okay. Hopping over to the other side of the project, we have the Silhavy Road intersection, and over on this side, we opted for an all-way stop that also provides a level of service B for all vehicles. And there is a little bit more variance for the turning radii compared to the Sturdy Road intersection, just to make sure that people have ample sight before they decide whether or not they're going to make their turn movement or not. And then once again, the deceleration, storage, and taper lengths were all designed via the Indiana Design Manual. Taking a look at the alignment, you can see that this alignment stays on the northernmost side of the Eastgate development to avoid impacting the intramural fields and the baseball field as much as possible. And it does feature 3 750-foot radii horizontal curves that were put in place to avoid wetland impacts for aesthetic purposes, as well as to keep driver speeds low. And off of that is a 140 space parking lot. So taking a closer look at that parking lot, you can see that there are 140 spaces in the parking lot, all of which have 10-foot by 20-foot stalls, with the exception of the 5 handicap spaces, which have 11-foot by 20-foot stalls. And along the parking lot, there is a 5-foot sidewalk that connects the entire length of the parking lot to the front of the building, so that people who come in for their commute don't have to travel through the grass or anything. In order to construct this, we had to come up with a maintenance of traffic plan that we decided to break up into 2 phases to not close down such a large section of important roadways within Valparaiso. And so for the first side of maintenance of traffic, we'll be constructing the westernmost side of the site, including the Sturdy Road and Chapel Drive intersection, and traffic will be routed along Silhavy Road. And then once this is complete, traffic will be switched over, and we'll construct the easternmost side of the project, as well as the Silhavy Road and Chapel Drive intersection. And traffic will be routed along Sturdy Road, and they will have the opportunity to drive through the brand new signalized intersection for the first time. Once all of the construction is said and done, this is kind of a final site overview of what everything will look like when it is put together. And in order to design all of this appropriately, we had to come up with a construction cost via the NDOT bid items list. And so the major costs that we had within this project were excavation, aggregate, and then the signalized intersection. And it comes to a total of about $3.3 million. And then when you add in the 20% contingency, it's about $3.9 million. And so with that, I will pass things along to Bella, our structural engineer.
Thank you, Lily. As Julie said, I will be covering the structural portion of the Eastgate Development Project. So the building design is a single-story steel building with an area of 42,000 square feet that will include classrooms, offices, labs, a covered outdoor space, and a 240 person auditorium with a stage. The decision to make a single-story steel building was decided in the preliminary stages, in which economics, feasibility, environmental concerns, and aesthetics were all considered, and this was decided to be the most suitable for the client. Taking a look at the roof framing plan, we see that there are varying beam and girder lengths, and this is a result of taking into consideration building components as well as existing buildings on the university's campus, as well as published values for different occupancy sizes and room sizes. And that's where you get the variation between all of the member lengths that we will take a closer look at throughout the presentation. And so looking at the design of the gravity system, we consider the dead and the live loads that will be acting on the building. As you can see in the chart, there were 3 main dead loads that were considered, because those are all of the components of the roof and the decking of the roof. However, we also considered 2 live loads. However, because you only consider the largest of the live loads for the overall design, you'll see that the roof live load was considered over the snow live load, and that was how all of the member sizes were determined. You will note in the 2 images on the screen that you can see that there are columns that have been removed. This is to accommodate the auditorium space and the office space. I wanted to highlight these 2 locations because throughout the building, there's a typical base size, although there are slight variations between member sizes. However, these are the 2 areas in which design components were slightly different and additional considerations were made. And so to highlight some of the additional considerations, there were pretty consistent columns throughout the building, as you can see by the lighter and the darker members in these 2 images. However, the highlighted columns are actually columns that were of larger size to accommodate the larger members that are spanning across these areas. These columns were used to not only support the self-weight of all the girders and the beams that are lying on them, but also the loads that were previously mentioned. And then shifting to the lateral design of the building, this is where we added the bracing members to ensure that the nodal deflections of the building were satisfactory based off of published codes. So you can see in the chart there, we considered seismic loading as well as wind loading to ensure that the members were able to support when these loads are acting on the building. So the braces that were added were W8x10 vertical braces that are tension controlled, and we'll take a closer look at the tension members in the upcoming slides. So to provide an example of a section cut of the building, you see the elevation views on the east-west side of the building. And these are the only two bracing members that were added, and they are on the exterior portion of the building. However, I will note that all of the braces that were added either on an exterior wall or on an interior wall throughout the building, so it wouldn't interfere with a space that had been allocated for rooms and hallways. Now to take a closer look at the north-south elevations, I'm again highlighting the auditorium space and then the office space in the next slide, where you see that bracing members were not added to interfere with the room space. However, braces were needed along the exterior walls of that large bay size so that the rooms could be properly supported and could withstand the loads. And a similar thing occurred with the office space. However, you will see that there was a slightly different bracing configuration, although that was what was necessary to support the loads. And also, I would just like to note that through these images, you can see that the elevation of the building is 20 feet from the top of the slab. And we will talk about the slab in the next slide, where we talk about the building foundation. So to take a closer look at the building foundation, you'll see that past the exterior columns, the slab actually does extend. And the design of this slab was a 3 feet design to make sure that we're accounting for erosion. And so in designing the slab, we considered all of the occupancy floor loads that would be acting on the building. However, as highlighted, the 150 PSF was used because the auditorium space will consider the largest load. The next after that would have been first floor corridors for school. So we decided to over design slightly just to ensure that the whole building would be able to satisfy, or this whole design would satisfy the entire building. So the thickness of the slab is 7 inches, and that was to ensure that between the ground floor elevation of the earth and the steel reinforcement that was used, there was a 3-inch cover, which is the minimum required. And then in order to support the loads acting on the slab, the design called for 2 layers of steel reinforcement, each in a different direction, to ensure that there was not failure in either direction. And for these steel reinforcements, we used number 4 bars that were spaced at 12 inches. And then jumping into the connections, we designed shear connections and tension connections. For the design, the shear connection was designed at the point in which the end reaction of the member was the largest, so that it would be determined satisfactory for the rest of the building. And so you will see that the bolt sizes as well as the plate thickness and the configuration were determined. An additional coping would be used for a beam to column connection to ensure that there was a flat surface in which the roof would be laid on. And finally, you'll see in the top image that a weld was designed between the plate and the column so that the connection will be connected. And a similar design was done for the tension connection, with the difference being only in the configuration and then the amount of bolts used, as well as the weld, as you can see in the image. And finally, to touch on the cost of all of this. So I put partial construction costs because the construction cost that I'm providing is only based off of the structural components that I have mentioned, which would be the beams, the girders, the columns, all of the bolts and connections, as well as the material for the slab, as well as the material for the roof. And as you can see in the image, that's the breakdown. However, I just wanted to kind of bunch everything together so it's easier to look at. And you can see that the final cost of all of these members is a little bit over 1.1 million. However, I will note that in the final cost that you will see at the end, I did use the RS mean square foot estimator rather than the line estimator that was used to determine all of these values, because that cost will give an overall design cost for the whole building, not just these components, because these components don't consider the walls and all of the finishes that make the true cost of a building. And now I will pass it over to Chance.
Thank you, Bella. So as Bella said, I'm Chance. I'm the lead on the structural concrete alternative. So just a quick project scope on that. So the main difference between my building and yours, mine is a 2-story building. It includes a restaurant as well as classrooms and offices. And it has an elevated walkway. So it's 2 separate buildings connected by a walkway. And I have a slightly smaller real estate. I'm at 26,000 compared to her. So the work completed by us. So we designed the floor plan. We determine all the loads, like where they're located, things like that. We determine the beam, slab, and column dimensions. We also determine the shear reinforcement and finally the cost. So here's some load coordinated views of the floor plan. So in green, you have your classroom loadings, in blue, your corridor, and in red, your walkway loadings. To be on the safe side, we went with blue, we went with corridor for everything, just to over design, make sure we're structurally sound. So then the loadings applied. So again, these are all the things we actually considered, but we ended up going with corridor just because that's what was applied to the building. You'll notice the restaurant load is bigger. However, that's located on the main floor. So we're not worried about that in the building. And then the hardwood floors, we included dead loads as well. This does not include lateral loads. That was imputed in RISA 3D, which has a risk category in wind to assess that. So the design requirements here, some ACI code that we use to determine our basic beam dimensions. So we looked at the beam width, height, and thickness to make sure it fell in between this. And then we took those parameters and input them into RISA floor to design an actual beam size that we could work with. So here are those actual sizes we could work with. So we have a length of 20 feet. That's for every vertical beam running in both the outside buildings. Those have a height of 18 inches and a width of 12. And then our walkway beams, we have a length of 32 feet, and each of which has a height of 28 and a width of 16 feet. Again, the walkway here is bigger because it has to span farther. So more load is needing to be carried. So here's our beam layout I was discussing. Everything vertical over here, that's all the 20-foot beams. That's in the exterior of both buildings. Located in the middle are your walkway beams. And then this floor plan here, this represents both the roof and the second floor. Both are designed in the same fashion. So here's our second floor beam schedule. The main thing to take away from here is the 2 highlighted rows. It's a little cut off, but 2 highlighted rows. So these moments here located at the top, that's what RISA basically told us the strength that was needed. And then down here's the strength we provided. So our goal was that we needed to provide more strength than what was needed so the building doesn't collapse. In order to do that, that became a steel selection process. So we recognized our moment we needed. We selected steel to meet adequate strength and then determined the strength provided based on that. Similar situation here for the walkway beams. You'll notice these moments are bigger values. Again, that's because it's a bigger span. It's 32 feet compared to 20. But again, our strength provided exceeds our moment, so we're good, we're structurally sound. And then our second floor shear reinforcement. So here is a typical section of one of the beams. We were able to space these stirrups uniformly. Typically, you cannot do this, but due to the low level of shear force that RISA provided for us, we were able to do it. So they were all spaced at 7 inches, with the exception of the 2 stirrups at each end of the beam, which were 3.5 into it. But again, this is just a diagram showing the shear reinforcement and why we were able to do that. Finally, our slabs. So we have 3 different slabs. We have a ground slab, floor slab, and walkway slab. You'll notice I left out the roof. The roof and floor slab are designed identically because the loads are very similar. So starting off with the ground slab, that's designed to span 3 feet. That's just in case there's problems with the soil, say there's erosion, things like that underneath the building. That way your slab won't fail. Walkway and building slabs are designed to span the distance in between the beams. So for the walkway, it has to span 20 feet, and for the building, it has to span 16. Additionally, we took into account for temperature and shrinkage, as well as strength steel in both slabs. And then finally, we have a cost estimate. As Bella mentioned, these estimates here are not based on any finishing. So this does not include drywall, flooring, any other finishings you'd find in the building. That's not here. This is strictly, in my case, concrete and rebar, given I'm reinforced concrete. So as shown in that table, that's the amount of concrete I used. That's the amount of reinforcement I used. So my rough line estimate is $1,612,000. And with that, I will pass it to Allison with water.
Hello, once again, my name is Allison Johanna, and I'll be covering the water resources portion of this project. As a reminder, for water resources, I was tasked with managing water quality volume and flood control volume within the site watershed. It's also an owner preference to treat that volume for that runoff for heavy metals, cadmium, copper, and zinc. And of course, we're looking to comply with local standards and requirements. Once again, here's an overall schematic of the practices. I'm not going to spend too much time on this slide because I'm going to delve deeper into each design. But one thing that I'm not delving deeper into is the grass buffer strips. So I wanted to note here that there will be grass buffer strips seen in green feeding off from the runoff from our new construction to the practices such as the rain garden, sand filter, and infiltration trenches. And those will have a width of 7 feet. Here are the design requirements and standards for the rain garden. And with this design, it has stayed relatively the same since our last progress presentation. And from the water quality volume, I found that it would have to have a required capacity of almost 3,000 cubic feet. And with the way that I designed it, it has an actual capacity of a little over 3,000 cubic feet. And for the emergency overflow weir, it would see a peak flow of 0.075 cubic feet per second. Sand filter design requirements and standards, which I then used to design the sand filter, which has once again stayed relatively the same. The required capacity of the sand filter was about 5,500 cubic feet. And with the way that I designed it, it can have an actual capacity of 6,700 cubic feet. To the emergency overflow weir, we have a peak flow of 0.75 or 0.15, excuse me, CFS. The infiltration trench design requirements and standards that I used to design the infiltration trench. I used a little bit of the Indiana design manual working with Jolie Overstreet because the infiltration trenches are also serving as roadside ditches. So as you can see by the cross section, they look very similar to roadside ditches. The required capacity based on water quality volume for the trenches is around 6,500 cubic feet. But because I have it running the entire length of north and south of the Chapel Drive extension, the actual capacity is a little over 46,000 cubic feet, which I think that this could help with flood control volume as well. For culvert design requirements and standards, there's really not much going on there, just that they should be capable of accommodating peak runoff from the 24-hour 50-year storm. But to be conservative, I ended up designing for the 100-year storm. As you can see here, I have 3 culverts to the east and the center, and then to the west going over Node Creek. For culvert 1, I found a peak flow of 1.07 CFS. I selected corrugated steel in a circular shape with a diameter of 1 foot. And as you can see on the figure on the right, this was generated by HY8. The water profile is seen in blue and it's not overtopping the roadway, which is what we're looking for. For culvert 2, which is in the center of the site, the peak flow was just under 2 CFS. I once again selected corrugated steel in a circular shape with a diameter of 1.25 feet. And once again, the HY8 generation found that the water profile would not overtop the roadway, which is what we're looking for. Culvert 3 to the west was a little bit different because it's passing through Node Creek and it also needs to convey the creek as well. So the peak flow was 125.9 CFS because the watershed is including all of the water that can flow into Node Creek as a whole. I once again selected corrugated steel in a circular shape. I have a somewhat larger diameter of 5 feet, and that comes from the passing through Node Creek. And with the HY8 generation, we see that the water surface profile does not overtop the roadway once again. For the detention basin, I designed it to look like this. I have 225 feet by 175 feet with a 4-foot depth, 4-to-1 slopes, which is typical. An outlet structure on the bottom of the basin, but slightly above because that's a requirement of the Valparaiso Stormwater Technical Standards Manual to avoid clogging. I've got 2 inverts coming from conveyance ditches, which will, in case of overflow, come from the rain garden and sand filter. And then I have an emergency overflow weir, which will then feed to a conveyance ditch that in case of overflow, this would flow to Node Creek. I also have the little schematic of the emergency overflow weir here. For the wet pond, I was looking at these design requirements and standards. The design's pretty similar to the detention basin. I've got it being 100 feet by 50 feet with a 4-foot depth, 4-to-1 slopes. The only difference here really is the outlet structure, which is slightly higher than on the detention basin, just to ensure maximum ponding, or not maximum ponding, minimum ponding, so that our wet pond is wet and staying wet. I've got an invert at the top coming from the infiltration trenches in case of overflow. And in case of overflow of the wet pond itself, I have an emergency overflow weir, which will once again feed into Node Creek. Here's a schematic of the overflow weir. For the conveyance ditches, so the Valparaiso Stormwater Technical Standards Manual does not specifically list conveyance ditches, so I ended up looking at the standards for vegetative swales because I found that it would be very similar. And you can see my conveyance ditches here, mostly for overflow of the practices that I've provided. I found that these ditches would have a peak flow of 0.31 CFS, 1% slope, and here's the cross section with a 1 foot bottom width, 2 foot depth to the one side slopes. Adding all of these practices together, I found that the overall construction cost estimate for water resources would be $770,000. Then for our team, we had a design cost estimate of $63,000. And for the overall construction cost estimate, adding all of our disciplines together, we had a little over 19.5 million, but with a 20% contingency, we're looking at a little under 23.5 million. For the Envision rating, we found that we had an 81 out of 86. The reason why we don't have quite an 86 is because some of the requirements were not applicable, not within scope, but we think that the 81 is still highly beneficial because we're providing several social, economic, and environmental impacts that will help this community and the Eastgate development. And with that, are there any questions? Yep.
So, a question about your infiltration trench. What's the media there, like underneath the surface?
For infiltration?
Does that have to be backfilled and you have gravel in there or?
Probably. Didn't specify what type of media, but because the majority of the soil in that area is clay, that obviously wouldn't allow infiltration. So it will have to be something that can allow for more infiltration. And I've seen like gravel, not quite boulders, but larger rocks doing it as well.
And then your storage capacity for the infiltration trench, is that below ground storage capacity or?
No, that is like with 1 foot of freeboard and within like the cross section itself. The entire length.
Why are you using the swales or the ditches for storage?
It's not really for storage, it's just to convey the runoff in case we have overflow in some of the practices, like it's not serving as any storage really. It's just for if the rain garden overflows and the sand filter overflows, to feed into the detention basin. And then, God forbid, the detention basin overflows, then that conveyance ditch would then feed to Node Creek. So it's mostly just for overflow, not really storage.
Didn't you use like a flow rate instead of like cubic feet? See, that's what threw me off, is
Oh,
just
okay.
when you use like volume.
Mhm.
So it comes to mind that you are storing water in it compared to here's the flow rate that can go through that swale or ditch in there. Another question about the culverts for you. What is the fill depth above those culverts, especially the one goes through the creek?
The one through the creek. I don't remember exactly off the top of my head, but I mean, if we look at the elevations here, it's looking to be about 10 feet. So I'm guessing it's that. I don't recall exactly though.
Okay, fine. Jolie, can you, being not transportation guy, what is level B and why is not level A? Why you want to go for a B instead of an A in the class?
So a level of service A is really hard to achieve in like actual practice and with design, like, because that's basically like saying you're perfect, but nothing in real life is ever actually perfect. And when I was analyzing all my intersection alternatives last semester, the only intersection alternative I found that I looked at that had a level of service A would be a roundabout at Sturdy Road and Chapel Drive, but it didn't make sense to use that alternative because of all the university buildings as well as the houses nearby. We would have to buy up a lot of property, and like obviously we would probably like have to take away part of Gellerson, and I know that you wouldn't want that. And then also roundabouts are really expensive and they have a lot of maintenance, so.
Is it about the cost or so what is the, when I say level A versus like level B, what, so for example, safety, additional stuff we get getting for getting level A versus B, for example?
It really just has to do with the intersection delay per vehicle, like the average intersection delay. But the signalized alternative versus the roundabout alternative, there was like a 1 second increase in delay between like the level of service A roundabout and the level of service B signalized alternative. And like, so really, I didn't think that that was like a big enough difference to choose something that's so much significantly more expensive and takes up so much more space for 1 second.
Then do you want me to ask you a question?
If you want to.
How high is your building in here? I'm trying to figure out how deep the girders, the long ones in the auditorium in here, and how much space that they will take out of the height of the building.
Okay, so originally, when I designed the building, I had done it with like a 12-foot height because I thought that that would be satisfactory just for like a normal person. But then when I realized that I would have all those large girders and beams, that's when I actually upped it to an elevation of 20. So the height of the building will be 20 feet because it's just a single story. So I figured even with all of the additions, because also if you think about an auditorium, if it's like a really expensive one, you'll have speakers hanging, you'll have stuff like that. And I wanted to make sure that it was able to accommodate anything that the client would want in it.
So how deep is the deepest girder in the building?
I think it might have been, trying to think, because I used those girders, I believe, were W30s. W30 by 60, I think. But I can't exactly remember what.
I forgot my steel design as it's been, but I saw like something like 33 by 118 or something.
I believe it should be in the section. But I'm sorry, I will get there. Sorry, W30 by 90 is the member that will be there.
So how deep is that? W30 by 90?
Off the top of my head, I don't remember, unfortunately.
6.
2'6", sorry.
Oh, around 2 for 6.
I know,
Thank you.
no problem. You want me to just pass it down the line or?
No, I don't have questions for Chad.
Other questions?
Is 5-foot culvert standard?
Tell me, I don't know. It's mostly the,
You got kind of went from like 12 to 18.
yeah.
2 foot, 4 foot, 6 foot.
Oh, like the standard sizes that you can buy it in.
Can you actually get one? Yeah.
I would guess that it might have to be specially fitted.
Or you make it bigger.
Yeah. Yes.
Can we go?
Hearing.
I have a question for Jolie across the Overstreet.
Okay.
On your intersection at Silhaven,
Yes. Let me go.
I saw some dimensions there. You clicked through quick enough and I couldn't.
Yeah,
You-
I figured I
For
wouldn't
example,
spend,
what is that 44?
so I'm not super happy with how the dimensions actually look, so I'm sorry about that. The 44 is the length of this storage for the through and right turn movement.
Oh,
So
okay.
it just kind of, it looks a little wonky, and then the 153 that it kind of overlaps with is the total length of this left turn lane, including like the deceleration, storage, and taper.
Okay, I just didn't see it.
Yeah.
So for the concrete structure, how does the slab connect to the beams, or does it sit on top? What is that?
Yeah, so it's on top of the beam. So when I designed the beams, I can go to a typical beam here. Sorry about that. Way. Yeah, so that H shown in the beam, that is the height of the slab and beam. So that's the 18 for the building. The slab itself has a height of 8. So then that is included on top of the beam. Then it's
Sitting on top of
so the whole height with the slab is 18, the total height. So there's not gonna be like, it's not a 28-inch height, it's a 18, including the slab between the beams.
I think that's all I had. You answered my question with one of your later slides. I was gonna ask you what direction your bracing I-beams. Which way did they go? Showed up in that later slide.
Any questions online?
I hope not.
I don't see anything in the
Yeah.
chat box.
They're a quiet group.
Thanks.
Go, go.
Yeah, pause.